Let's address the elephant in the room right now, BGP. BGP is absolutely massive. It's the protocol of the internet. It's what makes the internet work. And by the end of these series of skills, we're going to master BGP. And we're going to attack it by taking off small pieces at a time. By the end of this skill, we're going to understand how address families play a role within BGP, but we're going to get to that point by building up the basics and the fundamentals. Things like the difference between eBGP and iBGP, how neighbor relationships are formed, how networks are shared. I'd also encourage you to jump into the virtual lab and follow along with me. Typing the commands even over and over again are really going to drill home the concepts as well as how to configure these things, maybe even in an exam environment. It's going to be big, it's going to be fun, let's get going. To talk fundamentally about what BGP does is really to talk about what is even the point of BGP? Why do we even use it? We already have routing protocols, right? Like OSPF and EIGRP. So what makes BGP so different? Let me jump on a whiteboard and draw it up for you. So what even is the point of BGP? Where does it fit in the grand scheme of things? Well, this is the protocol of the internet after all, so we need to think about who runs the internet. The internet is basically run by service providers. Think about your local service provider. Maybe it's AT&T in the United States or Verizon in the United States, Virgin in the UK, or whatever your local telecom is. Just about every country in the world has a telecom or a service provider, and they're what provides access to the internet. But what is the internet? The internet is just a series of routers connected to each other who've exchanged routes. So let's focus on a service provider here like AT&T for a moment. I personally use AT&T, and I've got no qualms with them. AT&T, how many routers do you think AT&T has? If I were to write like R1 here, and then R2 over here. If you were to actually diagram out AT&T's routers, it would just go on and on and on and on and on. Just all the way down here. It's going to be massive. There's going to be redundant connections everywhere. You get the idea. Pretend for a moment then that AT&T is running an interior gateway protocol like OSPF or EIGRP, so that way all of these routers know how to reach each other. And then consider for a moment that AT&T probably has a large block of IP addresses, something like the 100.0.0.0/8 block of IP addresses. They then take this block of IP addresses and subnet them down everywhere. So all of these are having some sort of subnet in that block of IP addresses. Maybe it's subnetted all the way down to /30s. So down here is you. You may be connected into R2, and you may have a subnet of this block of IP addresses. What happens when you need to reach resources outside of AT&T? Maybe a resource in Verizon or a resource in the UK over on Virgin. If I were to draw that up here, and let's just say this is Verizon for a moment, Verizon would have a similar situation over here with all of these routers here, and they're all linked together. You get the idea. So you're trying to reach a server that's up here connected off of this router. If these two service providers were to use something like OSPF or EIGRP to exchange routes back and forth, it might work, but it probably won't. These protocols were designed to handle only so many routes. With all of these hundreds or thousands of routers that are going on in just one service provider, if a link were to go up or down and it would have to reconverge the entire network across these two service providers, it would just be too much for those protocols to handle. The solution to that would be to use an exterior gateway protocol called BGP. And BGP is what service providers around the world use. See, so far we've talked about AT&T and Verizon exchanging routes, but now we got to consider the fact that the world is bigger than our backyard. Routes learned in Romania are then shared through the EU over to the United States, then through to Asia. Routes in Africa are shared to the United States, maybe over to Europe, then to Asia, down to Australia. You get the idea. All of these service providers around the world have shared all of their routes with each other, and at the time of this recording, there are about 800,000 routes that make up the internet. So the way BGP would work in this case is AT&T, right here, would look at all of their collective routers in this block of IP addresses, and they would call this an autonomous system. I'll write it right here, AS for autonomous system. This makes sense because they have autonomy, they have control over all of their systems. And when Verizon, like this server up here, needs to get a packet into the autonomous system, AT&T can say, if you want to reach our autonomous system, which contains the 100.0.0.0/8 block of IP addresses, just send it to this router here, R1. Then from here, R1 would use the interior gateway protocol like OSPF or EIGRP, or even a variant of BGP called internal BGP, to route that packet through to its final destination. Similarly, you down here on this router need to access a resource in Verizon. Verizon may have something like the 200.0.0.0/8 prefixes. So Verizon tells AT&T, if you want to reach our autonomous system, which contains the 200.0.0.0/8 block of IP addresses, R2 here is going to be your next hop. So your packet comes into your router, who has learned about this autonomous system from R1, so it forwards your packet to R1. R1 sends it over to R2 in Verizon's autonomous system, and then Verizon's interior gateway protocol, like OSPF or EIGRP, knows the optimal path to route your packet to the server. So the point of BGP isn't to share tiny specific prefixes or subnets. In fact, most of these service providers won't let you share a prefix to them that is greater than a /24. So if you tried to say send AT&T here a /30, they would reject it. They would say that's too specific. That would overwhelm our routing table with too many specific prefixes. Please send us something like a /16. The point of BGP isn't to get you narrowed down to the specific subnet, it's just to get your traffic into an autonomous system so that it can be routed from there. So now that we understand the point of BGP, it's time to talk about how BGP really works. You're going to hear me say this a few times throughout this series, but BGP is a deliberate protocol. When I say deliberate, I mean there's not much dynamic discovery and changing happening here. You configure BGP to work exactly the way that you want it to work. So if you're thinking about OSPF or EIGRP, you may issue a network statement and then it starts trying to discover its neighbors. That's not the case if we were looking at AT&T and Verizon once more. Pretending for a moment that AT&T's autonomous system is Autonomous System 100 and Verizon's autonomous system is Autonomous System 200, when these two decided that they wanted to become neighbors and exchange routes, they would have to be explicitly configured saying that, hey, you are my neighbor and that is your autonomous system number. And the flip side would have to happen here. Verizon would have to say, you're also my neighbor, and I agree that your autonomous system, in this case, is AS100. What's even cooler about BGP is it uses TCP port 179 to make all of this happen. It's not using a multicast address, it's using TCP. So there is a reliable handshake that's going on there, and all of the other features that happen with TCP, like a time to live, or even the fact that this can be routed. Consider that an interesting point for a moment, that there may be routers along the way from R1 to R2. So if R1 sends a BGP packet destined to TCP 179 and destined to R2's IP address, this router would look at layer 3 information, pass the packet along to the next router, then pass the packet along over to R2, and all of these routers along the way, because they're never looking at layer 4, they have no clue that there's a BGP relationship going on. This is called the multi-hop scenario that we're going to talk about when we start talking about BGP's scalability issues. So we would explicitly configure who our neighbors are, and then beyond that, we explicitly identify each individual network that we want to share with that neighbor. Again, BGP is very deliberate. You tell it exactly how to behave in just about every single scenario. For this neighbor, you perform this action, but that neighbor, you perform that action. So at this point, we understand the fundamental purpose of BGP. In the next nugget, we're going to fire up a virtual lab and build our first neighbor relationship using BGP. In the meantime, that's been the point of BGP. I hope this has been informative for you, and I'd like to thank you for viewing. Now it's time to jump in the virtual lab and build our first neighbor relationship. This is going to be a pretty simple configuration, but what it's going to reveal very quickly is all of the subtle nuances that there are to BGP. And that's going to set up a lot more topics that we're going to talk about throughout the rest of this skill. Now let me jump on a whiteboard and demonstrate to you what the scenario is that we're configuring. This is the virtual lab topology that we're going to be working with throughout these BGP series, and what we're focusing on this nugget is this link right here, a link that exists from AS100 to AS200. In fact, let's zoom in a little bit so we get a better view of it. Yeah, there we go, that's a lot better. Okay, so what we have here is a scenario where we have a carrier here represented with AS100 and a different carrier here represented with AS200. It's not a stretch to think that there's a scenario where there may be a server down here with a public IP address that needs to be advertised out to the internet. So by establishing a peering relationship between these, we can now advertise the network for this server to a different carrier, who can then forward that advertisement out to a different carrier, or maybe off this link here. The flip side of that is maybe from AS200, there is a whole network of servers here. Maybe it's a data center. And from AS200, they want to advertise networks down to us. Now, like we said earlier, there's no dynamic discovery that happens in BGP. We have to specify the IP address of our peering router. We also have to specify the remote autonomous system, the autonomous system of the neighbor that we're peering with. Ultimately, the command looks something like this. We're going to specify the neighbor's IP address, then the remote AS, and their remote autonomous system. This command must be run before you can configure other aspects of your relationship. It has to specify what the IP address is of our peer and the autonomous system. But once this has been configured on both sides, they will begin immediately trying to form a neighbor relationship. And that's what we're going to set up in this nugget. So what we're going to work with in this virtual lab is we're going to be working with R2 and R4. Let's jump in the virtual lab and take a look at what we've got. So I fired up the virtual lab and we are working again with the link between R2 and R4. On both sides, this is using FA, Fast Ethernet, port 4/0. So I'll write FA 4/0 on both sides. And just as a reminder, R2 is going to be representing Autonomous System 100 and R4 is going to be representing Autonomous System 200. Why don't we get started getting a lay of the land and then fire up our BGP instance and build a neighbor relationship. For the time, I'm going to leave this writing on the screen. Just as a reminder, we'll run show IP interface brief, and we can see on FA 4/0, we're working with the 100.100.24, that's for router 2 and router 4.2 subnet. I'm not highlighting the mask right now because that's a very important factor when it comes to BGP. Now, on the other side of things, we can jump over to R4 by just clicking on the R4 tab, give it a show IP interface brief, and on FA 4/0, we see we got 100.100.24, again, for routers 2 and 4, and .4 to specify that we're using router 4. So let's start with router 2. To configure BGP, we're going to go and do configure terminal. We're going to type router BGP, and then it's not a process ID, it's not an area number, but it is our autonomous system. This is autonomous system 100 in this case. Before I do anything else, I want to point out that once you've declared this is my autonomous system 100, I can't specify another instance of BGP with a different autonomous system. If I try BGP 101 here, it says BGP is already running and you're in AS100. A router can only represent one autonomous system. So now let's jump into BGP 100. And remember, I said before you can do anything else, as far as neighbor relationships go, we have to declare who our neighbor is and what remote autonomous system they're in. While there is a network statement in BGP, it's not for discovery. We're going to explore the network statement in just a minute. Let's get our neighbor relationship stood up first. I'll use neighbor, then the remote IP address of our neighbor that we're connecting to. In this case, 100.100.24.4. And then remember what came after that? The remote AS. If I hit question mark, you can see there's actually a lot of things that we can set that deal with our relationship with this neighbor. But the one that we have to specify is remote AS. So let me tell it that the remote AS is going to be Autonomous System 200. So it now has the details of our neighbor relationship, and R2 is currently trying to form a neighbor relationship with them. It's using TCP. It's sending a packet to destination 179. Nothing's coming up yet because R4 doesn't know anything about BGP. Let's go ahead and configure this. We'll say router BGP. In this case, R4 was representing Autonomous System 200. And we know the neighbor is going to be 100.100.24.2, and the remote autonomous system is 100. Let's press enter. And look at that. After a few seconds, we see right there the syslog message, neighbor 100.100.24.2 came up. That seems really simple, but actually, under the hood, a lot happened. And this, my friends, is going to require a whiteboard because it's important. Let's draw this up like this. We've got R2, R4, the link between them, and we know that the network that we were working with here was 100.100.24.0. When we told R2 that its neighbor was 100.100.24.4, R2 knew that it was going to have to send a packet destined to this IP address and destined to port 179. In order to make it to this IP address, it looked at its routing table, or the routing information base, and in the routing table, it saw that it had a locally connected interface to that network. So while the destination portion of the packet was destined to 100.100.24.4, the source portion of the packet was sourced based on the IP address that was closest or that was in the routing table. In this case, 100.100.24.2. When R4 received this packet, it looked at the source IP address. Where was this source from? And it checked its BGP table to see if it had any neighbors configured with that specific address. Because we had typed the exact statement 100.100.24.2, it saw that this packet that came in from 100.100.24.2 matched a neighbor statement. It then validated that the autonomous system that was sent in that TCP packet matched the remote AS statement, which it did, and it knew that this was a valid neighbor that it could form a neighbor relationship with. The flip side happened over here on R2. When R4 sent a packet destined to 100.100.24.2, it checked its routing table, saw that it had a locally connected interface, and sourced its traffic to R2 from that locally connected interface, which was 100.100.24.4. Because R2 was configured to have a neighbor with that IP address, the neighbor relationship was able to come up. So now let's jump back into the virtual lab and verify our neighbor relationship just a little bit and set up some of the bigger nuances that there are to BGP. I'm going to run the command on R2 from privilege mode, show IP BGP neighbors. Well, the first thing we see our BGP neighbor 100.100.24.4, the remote AS external link. This is a big deal. There is a difference between external BGP and internal BGP. And that is what the next nugget is going to be all about. We should also take a look at the router ID. This is the remote router ID. By default, BGP picks the highest addressed loopback address. If there are no loopback addresses, it picks the highest address physical address. Timers are also a pretty big deal in BGP. The default hold timer on Cisco routers is 180 seconds. This means that our relationship, our neighbor relationship, will be valid for 180 seconds. And if we don't receive a keep alive in 180 seconds, we send out TCP messages that tear down the relationship. We say that the relationship is no longer valid. Now, keep alives are sent every 60 seconds, 1/3 of the hold timer. You may be thinking to yourself, coming from the IGP world, these are pretty long times, and that's quite frankly because BGP is so massive. There's so much that happens all the time with BGP because there's hundreds of thousands of routes out there on the internet that having any shorter times could cause floods of traffic. Our neighbor and us exchange capabilities. What are the things that we can send and receive? BGP has evolved a lot over time. In fact, I like to point out this 64 octet ASN right here. This is actually talking about the 32-bit autonomous system number. You see, when BGP first rolled around, we had 16-bit autonomous system numbers, meaning that our autonomous systems could go from 1 to 65,535. Clearly, there's a lot more service providers and a lot more autonomous systems out there now than there are 65,535. So they expanded it after the fact to a 32-bit autonomous system number, also known as a 4-byte AS. And now autonomous systems go up to 4 million... I'm not going to lie, I had to Google it. 4,294,967,295. Just like there's public IPs and private IPs, there are also public autonomous systems and private autonomous systems. We're going to talk about that in a later nugget too. We see that we are using the IPv4 address family. Again, we're going to tackle that later in this set of skills. We can also see some interesting statistics like our opens. That's what formed our TCP connections. Notifications typically happen when bad stuff happens. Updates, just like you would think. We're updating capabilities, prefixes, and networks. And we also see how many keep alives have happened with our neighbor. And by default, you would think this is a healthy amount of output, right? Let me clear the screen. You would think, yeah, this is some good output. There can't be a whole lot more to this show IP BGP neighbor command, could there? Well, let's hit spacebar. Now we get into the address family specifics, like what's happened for just IPv4 unicast prefixes. Scroll down some more. We can see some filters that have happened in this area. Keep on scrolling. Connection statistics. Keep on scrolling some more. And then we finally get to, yeah, this is a gigantic output that comes back when we do show IP BGP neighbors. And that's because you need to know this much info if you're a service provider trying to build connections to other service providers. So cool. We've got this neighbor relationship form, but it's not really doing much, is it? I mean, there's a neighbor relationship, but we're not sharing any routes with each other. Why don't we fix that? Let's just have a little fun here. I'll do a show IP interface brief, and we see we've got loopback 1 with an address of 2222. And you may have recalled earlier that I said that mask was going to play a factor in this. I think now's the time to demonstrate that. So let's share a route to 2222 to our partner through BGP. I'll go back into my BGP instance, and to share a specific route that we know about, we can specify the network command. It says, what's the network number? What's the network address? So in this case, I'm going to share 2222. We'll press question mark one more time. Now check this out. The thing that we're focused on here is we have to specify the exact subnet mask of the network that we want to advertise. There's no getting around it and doing something like 0.0.0.0, because if I press enter, look what happens. It says incorrect network or mask prefix length configured. When we advertise a route in BGP, it checks the routing table to make sure, first of all, can we advertise this route? And it has to specify the exact mask. So in this case, there is a 32-bit mask on this address. So I'll have to say network 2222 mask 255.255.255.255. Let's also advertise, just for fun, the IP address here of 172.16.12.2. We don't advertise a specific address. We actually advertise the subnet here. So if I give this a do show interfaces gig 00, I can see my subnet is 172.16.12. It's going to be .0/24. So hopping back into my BGP instance, I'll also advertise the 172.16.12.0 subnet, and I'll have to specify the exact subnet mask. There is a way that we can summarize these 172.16 addresses, and that's something that we'll cover when we get to route filtering. For now, I'll advertise those two networks, and we'll jump over to R4 to make sure that it's received those networks. Back in privilege mode, I'll run the command show IP BGP summary. I think this one's pretty important because we can see who our neighbor is, and right here at the end, how many prefixes have we received from them. We also see some pretty interesting things like what's their remote AS, how many messages have we sent and received. But right there, I see that I've received two networks from my partner over here at 100.100.24.2. So if I give it a show IP BGP just by itself, now I see the two networks that I've received. I also see their next hop location, and if I give it a show IP route to look at the routing table, I see I've got a couple networks here learned from BGP. So this sets up a very basic scenario of BGP. We formed a neighbor relationship. We explored how that neighbor relationship really came up by looking at the source address that came in from a packet versus what we had configured in our neighbor statement in the BGP router process. Validating that once those two matched, the source open packet and what we configured, the TCP session and the BGP session came alive. From there, we shared a network to our peer by specifying the exact prefix link that we needed in order to share that network. But this did set up a pretty big topic, which is what's the difference between external BGP and internal BGP, and that's what the next nugget's all about. In the meantime, that's been standing up a basic BGP session. I hope this has been informative for you, and I'd like to thank you for viewing. Up until this point, we've talked a lot about how carriers would connect BGP instances to each other. We had a scenario where maybe AT&T would connect to Verizon, and they would say what each other's remote autonomous systems are and what the remote IP addresses are. The neighbor relationship would come up, and they would share networks back and forth. We demonstrated that in the last nugget when we jumped in the virtual lab and did it. But what's actually really common is that a carrier may form BGP sessions within itself. It may have routers all across the world in its own autonomous system, and it would want BGP sessions existing by itself. So here's the real kicker though. When we form a relationship to a other institution outside of our autonomous system, BGP behaves one way, so to speak. When we form a relationship within our own autonomous system, when we have BGP peers within an autonomous system, BGP behaves differently. And that's what we're talking about when we say the difference between external BGP and internal BGP. Let's jump on a whiteboard real quick. When we talk about the difference between eBGP and iBGP, we are really digging into what are the nuances of BGP. In the last few nuggets, we looked at this scenario right here, when R2 peered with R4, and this was AS100 versus AS200. When we were on R2 and we typed router BGP 100, R2 became aware that its autonomous system was 100. And when we typed the neighbor command neighbor IP remote AS 200, R2 was smart enough to see that this 200 wasn't its own autonomous system, therefore this must be an eBGP connection. Let's now pretend we wanted to build a peering right here between R1. R2 enters router BGP 100, again knowing that its autonomous system is 100. We would type in the neighbor command IP address remote AS again, but this time we would type remote AS 100. And because R2 is so clever, it knows that this 100 for the remote autonomous system matches its own autonomous system, therefore it's going to form an iBGP connection. This really is the first nuance to eBGP versus iBGP. It's just knowing how it recognizes it's an eBGP versus iBGP scenario. R2 can recognize its own autonomous system versus what the neighbor's autonomous systems are and determine if it's an eBGP or an iBGP session. So before we dig any more into the nuances of eBGP versus iBGP, let's jump back into the virtual lab, and using some muscle memory here, we're going to configure the eBGP instance to AS200 and the iBGP instance within AS100. So I've fired up the virtual lab. I'm on R2. I'm going to jump into configuration mode so that I can configure BGP. So that I can configure eBGP. Let's configure the eBGP session first. I'll go into router BGP 100 because that's my own autonomous system. I'm going to try and connect to our neighbor again with 100.100.24.4. The remote autonomous system across the way is 200. Jumping over to R4, I'll go into configuration mode. I'll go into router BGP 200 because that's R4's autonomous system. And I'm going to configure my neighbor relationship with 100.100.24.2. The remote autonomous system is 100. After just a moment, I see the neighbor relationship has come up. If I give it a show IP BGP neighbors, in the very first section, I can see this is using an external link. I know this is an eBGP instance. Now I want to configure my iBGP instance between R1 and R2. If I give this a do show IP interface brief, R1 is configured off of Gigabit Ethernet 00. The format again is 172.16 12 here represents the link between R1 and R2, and 2 here represents the router number, in this case R2. So R1's IP address is going to be 172.16.12.1. I'll specify I want my neighbor to be R1 172.16.12.1, and the remote AS is not really remote at all. It's my own autonomous system, which is 100. Now let's jump over to R1 and get that neighbor relationship stood up. Jumping into config mode, we'll say router BGP 100, neighbor 172.16.12.2, remote AS, again 100. Doesn't take very long for that relationship to come up. If I hit end and then say show IP BGP neighbor, got to type correctly, I see we've got here an internal link, knowing that this is an iBGP session. So now it's time to introduce the next nuance of iBGP versus eBGP, and that's how routes are actually advertised back and forth. What I'm going to do is I'm going to jump over to R4, I'm going to jump into router BGP 200, and if I give it a do show IP interface brief, we can see there's a loopback here, loopback 4.4.4.4. Let's pretend for a moment that I want AS100, our eBGP peer, to be able to access loopback 1, 4.4.4.4. So you would think, cool, just to get this route into AS100, I'll just specify network 4.4.4.4 with a mask of 255.255.255.255, since the loopback addresses are 32-bit mask. Awesome. Let's jump over to R2. I'll jump out of configuration mode, and I'll give it a show IP BGP, and I see the 4.4.4. address. Can I ping 4.4.4.4? Yep, there we go, round trip. That's great. So it's not a stretch to think then that R2 would then send this network on to R1. From R2, I can also give it a show IP route. Let's just cut right to the chase, and I see 4.4.4.4 was learned via BGP. I'll also point out that it has an administrative distance of 20, which is the AD of external BGP. Let's jump over to R1 for a second. From privilege mode, I'll give it a show IP route. No 4.4.4.4. You see, I've got R2, which is connected to R1, and this is forming our iBGP session. And I've got R4 up here advertising its loopback. This is our eBGP session. Well, R2 clearly has the connectivity to the loopback. It knows of the route. And the next hop on that route to loopback 1 was 100.100.24.4. It's not a stretch to think that R2 then advertised that route to R1, don't you think? Let's take a look at what were the routes that we've learned from BGP so far with show IP BGP. Well, that's interesting. The route is there. But there's one very important symbol missing from show IP BGP, and that is this symbol right here, the best route. You see, we see that it is a valid route, and we see that it came to us internally. There's the little I there, but there is no best. And why? It's because of this right here. That next hop address is still R4's address. And as we see in the routing table above, there is no route to this next hop address. Let me just draw R1 and R2. This is the next nuance of iBGP versus eBGP, and it's setting up the next nugget, which is how do we solve this problem? When this route came in from eBGP, the advertising router, in this case R4, set the next hop to be its own IP address. eBGP advertised routes change the next hop address to be its own IP address. But routes that are forwarded through iBGP never change the next hop address. So the only way for R1 to have installed the route to 4.4.4.4 in its routing table is if it could reach the next hop address, in this case, R4's address. How do we fix this problem? That's what the next nugget's all about. In the meantime, this is setting up building an iBGP session versus an eBGP session and validating what's really going on under the hood. I hope this has been informative for you, and I'd like to thank you for viewing. In the previous nugget, we set up a pretty big nuance between eBGP and iBGP. When eBGP advertises routes to its partner, it will change the next hop address to be our next hop address. So if we're AS100 and we're advertising a route to AS200, we will set the next hop address to be our address that the router is coming from. So that way the eBGP peer knows how to get back to what we're advertising. But when it comes to iBGP, we're not changing the next hop address. So if a route comes in from eBGP, or if we learn a route from iBGP, we aren't changing the next hop address. That created a problem for us. Remember this problem? Yeah, remember this scenario here? When R4 advertised its loopback down to R2, it made sure to set the next hop address to be the exiting IP address towards R2. R2 received this route, had no problem because it could reach the next hop address, but then it sent the advertisement over to R1 naturally, but it didn't change the next hop address. Because R1 can't reach this interface on R4, it didn't install the route in its routing table. It said, this isn't going to work for me. This isn't a best path. So what we need to do is we need to get R2 to change the next hop address to be its interface. And luckily for us, this isn't that hard of a task to accomplish. So firing up the virtual lab, we can jump over to R2. And my challenge to you is stand up the virtual lab, getting it to a point where it's formed neighbor relationships and R4 is sharing its loopback address. This is great for really nailing down the commands and building that muscle memory. Once that stood up, we can go back into R2, router BGP 100, and now we can alter how our relationship with R1 works. Routes that we advertise towards R1, we can automatically tell it to change the next hop address to be our own address. The command looks like this. We'll specify our neighbor of R1, 172.16.12.1, and then we'll specify next hop self. Press enter, and that's it. We've done the trick. Now routes that we advertise only to this neighbor, that's a key thing about BGP. Remember, BGP is super deliberate. It's not going to set next hop self everywhere. It's only going to be the neighbors that we specify. Now, in this case, the routes that we send over to R1 will have a next hop address of our exiting address. So if I jump back to R1, I'll run show IP BGP again. And we do have to wait sometimes for this to refresh. Let's give it a minute to refresh. There we go. Look at that. Now we've tacked on the little sideways caret there that we've needed that says this is best. And if I check out show IP route, I now see that this route has been installed. Let's take a look at the topology one more time. We've got R1, R2, and all the way up to R4. What I propose we do is I propose we advertise the loopback address on R1 up to R4. R1 will advertise this address naturally over to R2 with the correct next hop of R1's address. But because R2 would then advertise it via eBGP, it would change the next hop address going up to R4. So clearing the screen, I'll go into configuration mode. We'll go router BGP 100. And we'll specify our network 1.1.1.1, mask of 255.255.255.255. Press enter. Let's jump over to R2. Let's give it a show IP BGP. I see that we have learned about 1.1.1.1, and it's got a correct next hop address. Let's verify that we can ping 1.1.1.1. Looks good, round trip. And because we understand how eBGP versus iBGP works now with next hops, we don't have to specify a next hop self when we're going towards R4. That's an eBGP relationship, and routes that we've learned internally through iBGP will be advertised out externally with the correct next hop. So if I go to R4, I'm going to run show IP BGP, and look at that. There's the valid route to R1 with a next hop address using R2's next hop address. So from R4, if I ping 1.1.1.1 and make sure to specify a source of loopback 1, hey, look at that, round trip. We have now conquered one of the big nuances of eBGP versus iBGP, and that's how the next hop address is handled. While we've got this output pulled up from show IP BGP, it's now time to talk just a second about how it chose to send that route. How BGP chooses what's the best path to send something to is quite complicated. There are a tremendous number of factors going into it. Things like the weight plays into it, the local preference plays into it, the metric plays into it. But if we don't change anything, what it defaults to is the path. You know how RIP chooses the best path is by hop count from one hop to the next, and the least amount of hops is how it chooses the best path in RIP. Well, BGP isn't terribly unlike that. It looks at hop count, but for ASs. It's kind of like the AS hop count. And what we're looking at here in path is the paths of ASs that it traverses. So maybe one day we'll see a path that looks like 200, 100, I. From the router's perspective, this would go through Autonomous System 200 before it gets sent to Autonomous System 100. Every time an eBGP advertisement takes place, the exiting autonomous system is added to the list. And the receiving router then sees how many paths it has to go through. All of these things here that we're looking at are called path attributes. So when a network statement is run, it advertises the prefix plus path attributes. The prefix and path attributes combined together are called an NLRI. That stands for Network Layer Reachability Information. Now, we're going to dig into this stuff, especially path attributes, a lot more when we start talking about filtering with route maps, as well as manipulating the best path algorithm. What I wanted you to see now is, first of all, how eBGP versus iBGP handles the next hop address, as well as how it determines which path it's going to install in its routing table. The next nugget is going to dig a lot more into how NLRIs are both received and sent on a router running BGP. In the meantime, that's been further understanding eBGP versus iBGP. I hope this has been informative for you, and I'd like to thank you for viewing. This right here is where BGP steps it up a notch. How BGP handles incoming and outgoing routes to and from which neighbor is kind of a big deal. Understanding the process that BGP takes towards bringing routes in and sending routes out is going to be critical for you to master BGP. So let's jump on a whiteboard and let me show you the diagram of how routes flow through BGP. At the end of the day, BGP does three things. It brings routes in, it processes those routes, and it sends routes out. There's three separate databases that handle those three things. I'm going to circle those three databases right now here in blue. This is the RIB-in. This is the local RIB. You can see they call it BGP database right here. And then this is the RIB-out. These are the three databases. There are show commands to view the local RIB and the RIB-out. There is not a show command to view the RIB-in. Why? Because so many routes come in and so many routes are processed that after the routes have been processed, this table gets truncated, or a fancy way of saying it's emptied. So you could run a show command, but there wouldn't be anything there. So this is where we're going to start. We're going to start our journey. I'm going to change my color here so it doesn't get confused with the databases. Starting the journey right here with routes that come in from up here. This is either an iBGP or an eBGP. They've typed in the network command on their side and they've sent us an NLRI. Recall, that's a prefix as well as path attributes. The NLRI is stored in the RIB-in, and then inbound route policies are applied to the RIB-in. You're going to learn a lot more about these policies when we get towards filtering BGP. These are primarily route maps, but they can be distribute lists, prefix lists, and autonomous system ACLs. They could be filtering routes out, or they could be adjusting path attributes. They could be setting a new weight or a new local preference. Once the inbound route policies have been applied, they go into the local RIB database. You've seen this. This is show IP BGP. Remember when we were troubleshooting why R1 couldn't reach R4? It showed the route, but it wasn't a best route because it had a next hop path that we didn't understand. That we were looking at this database right there. Right here is why that route wasn't installed in our routing table. At the time, R1 couldn't reach R4 because R2 had sent us that prefix but didn't change the next hop address. Because the next hop wasn't valid, it never got sent down here to install routes in the global routing table. Remember what we had to do is on R2, we had to change the next hop address with next hop self because that's the behavior of iBGP. Once we did next hop self, it passed the next hop and validity check and identified the best BGP path. Well, there was only one path, and that was to AS200. So the route was installed in the global RIB. The flip side of that is we advertised the 1.1.1 address over to R2, who then advertised it up to R4 because there was no outbound policy stopping us from doing that. The route was installed into the outbound database and then forwarded to a peer. Now, this show command is not one that we've seen yet. Let me bring up the virtual lab and show you what that looks like. From privilege mode, if you want to see the routes that you're sending outbound towards a neighbor, we can do show BGP IPv4 unicast because we are advertising an IPv4 unicast address. I'll give it a question mark. And we can specify our neighbor right there by specifying neighbors. So I'll say neighbors 100.100.100, 24.4. And then we can specify the property of advertised routes. Look at that. This is showing us the outbound database for a specific neighbor. Yes, there will be a separate database for every neighbor, but it does show us what routes we are advertising towards R4 in this case. Now, that example was particularly interesting because we learned about 1.1.1.1 from R1. This was brought into the inside database. There were no policies processing it out. It was dumped into the BGP database. We had a valid next hop. The best path was identified because there was only one AS to traverse. We had no outbound policy stopping us from sending it outbound, so we sent it outbound towards R4. Whoop, there we go. What if we had issued our own network statement? If you notice when we issue our own network statement, it first checks to make sure that that network exists in the routing table. Remember when we were specifying masks earlier, we couldn't just specify like a range of addresses. We had to specify a specific address that we could send out. We could only advertise networks that we actually do know about. Once it validated that the routes that we were advertising with the network statement were in the routing table, it goes ahead and puts it into the local RIB database. So none of this part is happening. There is no RIB in when we specify a network statement. Why does this process matter? Because you need to know when policies are going to be applied, and you also need to know about these steps in order to troubleshoot things that are going wrong with BGP. Now you can look at what routes you've received and figure out maybe why they're not in the routing table. Or you can validate that you did send a route to a peer and have them look into it too. This has been understanding the BGP process. Critical steps to understanding your BGP journey. I hope this has been informative for you, and I'd like to thank you for viewing. The iBGP nuances don't just start with how routes are advertised to and from each other. iBGP best practices dictate several different things to us. One of those best practices is that peer relationships, neighbor relationships, can and should be formed based on loopback addresses. Let's jump on the whiteboard. Let me show you what I mean. Here's the scenario. We are AS100. These are all of our routers. We've got 4 routers on the board here, and we are going to form iBGP relationships between them. Now, because these are also our routers, we have an IGP already running in between them. Maybe it's running something like OSPF. So we have connectivity around the horn, and they even know about each other's loopback addresses. So R1 has a loopback of 1.1.1.1. R2 has a loopback of 2.2.2.2. R3 has a loopback of 3.3.3.3. And R4 has a loopback of 4.4.4.4. R1 can ping 3.3.3.3, 4.4.4.4, 2.2.2.2, and so on. So here's what I want to do. I want to form an iBGP relationship from R1 to R2, and I want this relationship to exist between my loopbacks. Basically what I'm saying is when I issue my neighbor statement, I'm going to say 2.2.2.2, then the remote AS of 100. And on R2, I'm going to issue my neighbor statement of 1.1.1.1 and the remote AS of 100. Can you see where the problem may come in here? Recall when R1 and R2 send each other open packets, meaning let's open our TCP 179 connection to each other. Let's open our BGP session. How did it determine how to do that? In this case, R1 issued the 2222 statement. It looked in its routing table and it saw the exit interface right here. So the source packet is going to be 172.16.12.1. Now, when R2 receives that, it's expecting the source address to be 1111, not 172.16.12.1, and the neighbor relationship doesn't come up. Let's verify this by jumping in the virtual lab right now. So the first thing I actually need to do in the virtual lab is I need to stand up OSPF between these devices so they know how to reach each other, including those loopbacks. From R1, we'll go into configure terminal, router OSPF1, and we'll just say grab everything, 0.0.0.0. Oops, too many zeros. 0.0.0.0, area 0. Cool. Then on R2, we'll do the same thing. Router OSPF1, network 0.0.0.0, 0.0.0.0, area 0. Cool. We'll give it just a moment to converge. And there we go. There's the syslog message, says that we've gone from loading to full. If I give it a show IP route, I can see I can now access 1111 from R2. We'll ping 1111 and verify. Yep, there we go. Round trip looks good. Okay, let's start building our BGP neighborship with R1, but we're targeting a neighbor of those loopback addresses. So we'll say router BGP AS100, neighbor is going to be 1.1.1.1, remote AS is 100. I'll jump over to R1, issue effectively the same commands. Let's exit out of router, there we go. BGP 100, neighbor is going to be 2.2.2.2, remote AS is 100. At this point, you would have expected the neighbor relationship to come up. Jump back to privilege mode. We're going to turn some debugging on. We'll do debug, BGP, IPv4, unicast, and just press enter. There we go. We've got some activity opening here. I'm going to do an undebug all, and here's what we're seeing here. This is some pretty interesting output. Right here, this line. We've gone active. We went from idle to active. Active means is actively trying to build a BGP relationship to each other. But it's failing because the source address that it's coming from doesn't match what's in our BGP neighbor relationship table. We have to change the source address that we're advertising from. Just like everything else with BGP, this is neighbor-specific stuff. So what I can do is I can go into configuration mode, router BGP 100, and we can say for neighbor 2.2.2.2, update source, meaning what is the source address that we want to come from, and we specify a specific interface. In this case, loopback 1. Over here on R2, I'm going to do the same thing. I'm going to say neighbor 1.1.1.1, update source, meaning change my source address to be loopback 1. And while that's going on, I see the neighbor relationship comes to life. There we go. I see the neighbor relationship comes up on both sides. So why does this matter? Why did we do this? We now have an iBGP relationship from R1 to R2, thanks to because we're using loopbacks and we've changed the update source that it's coming from. If we had done it based on these physical addresses right here, this would have been cool and it would have been great until this link died. Then we'd be scrambling to rebuild an iBGP relationship. But because we used loopback addresses, this link can die, and the iBGP would tell us a new path to go through the network to get to our BGP near. We wouldn't have to reconfigure BGP. We would just have to wait for OSPF to reconverge, which probably will happen in less than the time that the hold timer will expire. So that's been why we use and how we use a new source address when building our neighbor relationship. I hope this has been informative for you, and I'd like to thank you for viewing. You may have noticed up to this point, I haven't issued the show run command once during the series, and that's been on purpose. There's a lot more going on under the hood than you may have been aware of, and that's because BGP uses address families, and it made some of these decisions for you behind the scenes. When we jump into the virtual lab, you'll see pretty quickly what those were. But let's talk about address families for a second. What are address families after all? BGP, when BGP is running, runs with one process, one BGP process for the autonomous system. But under the hood, it actually handles different address types. There's IPv4, there's IPv6, there's even something called VPN-v4, which you're going to learn about when we get into MPLS Layer 3 VPNs. Super cool. I've watched it. Some of the best stuff you'll ever see. Beyond that, there's something called sub-address families too. There's IPv4 unicast and IPv4 multicast. And there's IPv6 unicast and IPv6 multicast. Now you'll notice when we were working with BGP, we haven't really specified any of that. That's because BGP made some assumptions for us. Let's jump in the virtual lab and let me show you. I'm on R2 right now, and my challenge to you as you fire up the virtual lab is to rebuild the connection between R1 and R2 as an iBGP relationship using loopback addresses, and then build the eBGP relationship between R2 and R4. Okay, at this point, I have a couple neighbor relationships fired up. I can see my neighbor with 1.1.1.1 came up, and my neighbor with R4 came up as well. If I give it a show IPBGP, I can see a couple routes have been advertised and installed. The 2222, that's R2's loopback, shows the next hop of this machine right here. And the R4 loopback, 4444, there we go. It's advertised right there. So if I look at the history of commands that I've run here, I went into router BGP. I issued a neighbor statement, a couple neighbor statements here, and I issued one network command. If I actually do show run, and I'll say section BGP, I see those commands. That's not what actually happens on newer versions of iOS. Newer versions of iOS automatically move these statements into address family categories. Here, let me jump into config mode, and I'll delete out this entire config, and I'll show you how this now works. No router BGP 100, I see all of the neighbor relationships come down. I'll go into router BGP 100, and the first thing I'm going to tell this BGP instance is don't default everything into IPv4. You see, by default, all of our network statements, all of our neighbor statements, they're defaulting into the address family of IPv4. We don't have to explicitly say, use IPv4 for this connection, use IPv4 for these policies. So the command that we run is no BGP default IPv4 unicast. Now I can build my neighbor to R1, specifying 1.1.1.1, the remote AS of 100, and I'll specify that I want my source to come from loopback 1. But interestingly, the neighbor relationship doesn't come alive now. If I jump over to R1, let's give it a show IP BGP neighbors, and we see that the state is still idle. We don't have any neighbor sessions yet, and therefore we don't know what our neighbor's capabilities are. But if you recall way back when, one of the very first times we ran this command, one of the capabilities was address family IPv4. We need to activate this capability for our neighbor in order for this neighbor relationship to come to life. So jumping back to R2, we can now specify which address families we want to work with. So if I do a question mark, you can see what kind of address families we have. We have IPv4, IPv6, and again, VPN v4. I think that's an interesting one to work with. Let's take a look at IPv4, and then question mark one more time. We have to specify the sub-address family of unicast. You can see the terminal's now moved into address family configuration mode, and now I have to explicitly say for neighbor 1.1.1.1, activate the IPv4 address family. And boom, the neighbor relationship comes to life. Beyond that, any networks that I want to advertise, I have to advertise them from the address family command. So if I want to advertise 2222, I have to advertise it from here. This address family section is also where you would perform other actions like redistribution. So if I wanted to redistribute, say, IPv4 learned routes from OSPF into my BGP instance, this is where I would redistribute them into BGP. So now similarly, let me exit out of address family mode. Let me bring up my neighbor relationship, again with R4. Recall that I do have to go into the address family of IPv4 unicast in order to activate this. Specify activate, and in just a moment, that neighbor relationship will come to life. There it is. Let me exit out of this address family mode and also point out one more thing that will play a critical factor in your success as a BGP engineer, is that when you go into IPv4 unicast, this is specifying the global route table. Remember this diagram right here? Once routes have been received from the local RIB, either the network statement or from peers, the next process is a next hop validity check. Well, why would that run an issue to you? If I were to issue a network statement in address family IPv4 unicast, but that network didn't exist in the global RIB, it existed in a VRF, we would have a problem. It would not exist. It would fail the RIB check right there. So if I wanted to say share routes that I've learned or redistribute routes that I've learned from a VRF, jumping back to the virtual lab, I would have to specify address family, IPv4 unicast, then you can specify the specific VRF here. I'll just put my VRF. Now, I don't have a VRF there. It tells you my VRF doesn't exist, but that's how you would go and configure addresses and BGP handling with relation to VRFs. Beyond that, we can go into address family IPv6, as long as IPv6 is enabled on the router. Let me fix that real quick. IPv6 unicast routing. Now we can go back into router BGP 100. And for real, we can go into address family IPv6. And you could activate IPv6 addresses and IPv6 advertisements from within this address family here. The commands, the behavior, the BGP process for IPv6 and IPv4 is identical. So now if I end this, go back to privileged mode, do a show run section BGP, it looks a little bit different, doesn't it? Now we've disabled the default IPv4 unicast section. We specify our neighbor relationships, then we move into IPv4 where we activate those neighbor relationships and specify our IPv4 networks that we're going to advertise. Keeping in mind that this address family is tied to the global RIB, so when we advertise network addresses or receive networks from these peers, that's where we're checking it against. Also keep in mind that starting with later versions of iOS, this behavior is the default. So if you jump in here, specify a neighbor, then a network command, then run show run, it will show up with the address family and activate already populated for you. So that's been address families in BGP. I hope this has been informative for you, and I'd like to thank you for viewing. So that's it. Now you know everything about BGP. Don't you wish? That's okay, though. We've learned a lot about BGP, the nuances that go into BGP, iBGP versus eBGP, updating the source address, what address families even do, how routes are advertised from eBGP to iBGP, and so on. It's really, really heavy and really cool stuff. But what we're going to do next in the upcoming skills is the really exciting stuff with route reflectors, confederations, and filtering. So that's been getting started with the basics of BGP. I hope this has been informative for you, and I'd like to thank you for viewing.